Hello friends, thank you for your watching. Today I am talking about spin entanglement in two-proton emission with time-dependent three-body model. My original paper is now under review and its preprint is open in archive here. Two-proton radioactivity was observed in 2000, and this is the famous picture of iron-45 nucleus decaying at this point by emitting two protons. In such two-proton emissions, so-called diproton correlation has been expected to exist. Here, the diproton and dineutron correlations mean the quasi-bound state of two protons and two neutrons inside finite nuclei, and they are expected to keep the spin singlet configuration, which plays an essential role in today's topic, namely the spin entanglement. This is a brief summary of experimental searches for two proton and two neutron emitters. Experimentally, several methods like these have been utilized to explore the two proton and two neutron emitters. And if you are interested in more details, can be found in my PhD thesis here. So let me explain my motivation today. If the emitted two protons are in their spin singlet state, like this, a strong entanglement in terms of CHSH inequality, actually this inequality is expected. And here, this CHSH inequality is indeed one variant of Bell's inequality. And this acronym CHSH means these four people write this original paper. So if you are interested in, please refer to this original paper. And if such a nuclear spin entanglement exists, that can be the first example of natural entanglement in contrast to the other quantum entanglements produced by the more or less some artificial manipulations for photons or electrons or blah blah blah. And second, if such a nuclear spin entanglement exists, that can be useful as a probe to investigate the nuclear pairing correlation. Okay, let's learn about CHSH inequality or examination. First, I introduce two of my friends, namely Alice and Bob. And each of them measures one spin of the emitted two protons. The point of CHSH examination here is that they use several options for this polarization angle. Alice measures by using the two options, namely 0 or 2 theta for the polarization angle. On the other side, Bob uses plus theta or minus theta for the polarization angle. Thus, there are four options of measurement in total, namely A1, B1, A2, B1, A1, B2, and A2, B2. By using these four observables, the CHSH indicator, that is actually the spin correlation function, is determined by these formulas. According to the quantum mechanics, the max value of this CHSH indicator is 2 by square root 2. And this max value is realized if the two-particle state is one of the Bell states. Here I give the four members of Bell states. And for example, if the two-particle state is purely spin singlet here, the CHSH indicator becomes 2 by square root 2 when the polarization angle theta is 1 pi over 4, 3 pi's over 4, 5 pi's over 4, or 7 pi's over 4. And this is a simple mathematical exercise, and you can try to prove it by yourself. Remember that this conclusion is naturally obtained from the quantum mechanics. Next, let me also explain about LHV, namely local hidden variable theory. If this local hidden variable theory exists, that CHSH indicator cannot be larger than 2 indeed. Here I briefly give its proof. And if you are interested in, please stop this video and you can follow these details. Or you can refer to this original textbook. Anyway, from these discussions, the CHSH indicator is always smaller than 2 as long as so-called local hidden variable theory is working. However, in many experiments by using entangled particles, the CHSH indicator being larger than 2 has been confirmed. That means such a local hidden variable theory has been shown as phantom. Now, you may ask that can nucleons become really entangled? Actually, the answer is yes. Here, I introduce one remarkable experiment by Sakai and his friends in 2006. There, they measured the entangled two protons, which were produced in the deuteron-proton scattering here. And this figure shows that the spin correlation measured, namely the CHSH indicator, and this is larger than 2 at this point. Namely, a strong entanglement between the two protons was observed. Now I move to my own topic, the two-proton emission. And today I will discuss the two-proton emission from this beryllium-6 nucleus, which is the lightest two-proton emitter. One remarkable point is that this system can be a prompt two-proton emitter, namely the alpha proton resonance in lithium-5 is higher than this two-proton resonance of beryllium-6. Therefore, the sequential 1p 1p emission is energetically suppressed. And hereafter, my calculations are based on this three-body model of alpha particle as the core and two valence protons. This is the Hamiltonian of this three-body model. Because of the three bodies, the Hamiltonian includes both the alpha proton and proton-proton interactions. For the alpha proton interaction, the Wood-Saxon and Coulomb potentials are employed, and their parameters are tuned to reproduce the one-proton resonance of lithium-5, namely the core nucleon subsystem. For the proton-proton interaction, on the other side, nuclear and Coulomb terms are used. And the bare nuclear potential is the 2 Gaussian potential. Yeah, here I wrote. And this is tuned to reproduce the scattering parameters of 2 protons in vacuum. Then, this additional term is also necessary to reproduce the experimental 2-proton energy of this beryllium-6. Okay, the Hamiltonian is determined. The next question should be how to describe the 2-proton emission. For this purpose, I developed the time-dependent calculation. First, I modify this core proton potential like this, the wall potential around the alpha core. These figures indicate the 2-proton initial state. From this right panel, you can find that the 2-proton wave function is well confined around the core, namely inside the potential barrier. Notice also that this peak in the opening angle distribution, that means the diproton correlation, namely the spatial localization of 2 protons and the dominance of the spin singlet configuration. Okay, once this initial state is determined, the time-dependent calculation can be performed according to this formula. For more details of this time-dependent calculation, please see my original paper in archive. Now, let me show my results to you. This is the time development of so-called decaying state of the emitted two protons. Here, the decaying state is determined as the projected state into the initial state. And remember that the initial state was well confined inside the potential barrier. Therefore, this decaying state describes the outgoing component, namely the emitted component of the two-proton wave function. And this left figure, I plot the density distribution of the emitted two protons as a function of these two distances, namely one is the distance between two protons, and another one is the distance between the alpha core and the center of mass of two protons, and those are in x and y axis. And here you can see the main peak around RPP is 5 and RCPP is around 10, and that means the relative distance between two protons keeps around 5, and whereas the total distance from alpha core to the two protons, the center of mass of two protons, is going outside. So this means the two protons are emitted mainly to the same direction. In this middle figure, I plot the same function, but as a function of R1 and R2. Those are simply the distance between alpha core and proton 1 and alpha core and proton 2. And again, you can see that R1 and R2 are in the same value. The distribution is dominant when those are in the same value. So that means, again, the two protons are emitted at the same time to keep the same similar distance from alpha core. Finally, in this right figure, I plot the same function, but by integrating the variables of radius, and thus the distribution is on the function of only the opening angle between two protons. And here you can see again the dominance of spin singlet configuration, and the opening angle between two protons is really narrow. That means, okay, again, you can understand that two protons are emitted to the same direction by keeping the spatial localization. We are now close to the final conclusion today. Here, this upper figure indicates the decaying probability, which is determined from the total integration of the decaying state plotted in the previous panel. Again, here one can find that the present two-proton emitting decay is dominated by this spin singlet configuration. And finally, in this lower panel, I show the calculated CHSH indicator, or nothing but the spin correlation function calculated in this time development. And here you can understand that the CHSH indicator becomes larger than 2. Actually, the exact value is around 2.65 when I was using the model parameters to reproduce the experimental two-proton energy. Therefore, a strong entanglement is predicted. And actually, by changing this parameter FPP, which is nothing but this additional factor on the proton-proton interaction, I also confirmed that this spin entanglement is sensitive to this to the strength of this two-proton interaction. In this table, I summarized that results, and okay, by using exact one value for this FPP in order to reproduce this experimental two-proton energy, okay, the CHSH indicator is around 2.7, which is enough larger than 2, and thus, in terms of CHSH examination, we can say that this is a strong spin entanglement. On the other side, if I weaken this proton-proton interaction by using smaller values of FPP, this CHSH indicator becomes reduced and reduced. And at a certain point, it becomes lower than 2. And here, in this case, yeah, I can see that the entanglement is destroyed. It does not exist anymore. Summary of my talk today. The two-proton decaying state from beryllium-6 is suggested to have the dominant spin singlet component, and thus a strong spin entanglement is expected there. For future interests, those include, first, whether the two-proton spin entanglement can exist in other heavy two-proton emitters. Second, does this entanglement depend on the initial two-proton state, especially with or without diproton correlations? Third, how about for two-neutron emitters and proton-neutron emitters? Those interests are in progress now for reporting in future. That's all for today. Thank you for your watching.